Okay, this section should be a review because this topic is officially covered in Chem 1A. But I know from all the fun you had balancing the green salt equation that we need a review. So here we go. So we learned about oxidations and reductions in Chem 1A. And we learned a mnemonic oil rig. Oxygen is loss of electrons. Reduction is gain of electrons. And so that's one way to remember what oxidation and reduction are. Another way, which is just a slightly different definition, but you end up with the same answers. Oxidation is an increase in the oxidation state. Reduction is a decrease in the oxidation state. Reduction is a reduction in the oxidation state. Remember that? So if the oxidation state goes up, you're getting oxidized. If it's reduced, you're getting reduced. So we can look at the reaction between calcium and water. And if we assign oxidation states, we see that calcium, being an element, has an oxidation state of 0. The hydrogen in the water has a +1, each of them does, and the oxygen has a -2 oxidation state. And remember that oxidation states are a made-up concept. Because reduction is a reduction in oxidation state makes a lot of sense to me. Because it's in the word, the name of it, reduction. Okay.
I was looking at it because it didn't make sense with the oil rig.
Oh, no, so this is one definition. Oxidation is loss of electrons. This is looking at changes in oxidation state. So we can look at change in oxidation state, or we can look at gain or loss of electrons. So these are the oxidation states of the reactants. And after the reaction occurs, calcium now has a +2 oxidation state. Oxygen is still -1. The hydrogen over here is still +1, but we formed some H2 gas, which has an oxidation state of 0. So we can look at the calcium, and it went from 0 to +2. Its oxidation state went up. It was being oxidized. In terms of electrons, how does calcium become a +2 ion? It loses 2 electrons. Oxidation is loss of electrons. And here, some of these hydrogens went from +1 to 0. In terms of electrons, how do they do that? They gain an electron, right? Reduction is gain of electrons. Looking at oxidation states going from +1 to 0, the oxidation state has gone down. Okay? So when we have redox reactions, what makes them a little bit tricky is that the mass and the charge must balance. And there are some equations that you can get all the masses to balance, calcium atoms and hydrogen atoms, but it's not actually reflecting what's happening because you'll end up with the total charges being different. And so the best way to balance redox reactions is by breaking them into 2 half reactions. We balance those individually and then add them back together. This is the only method that's taught in the book, and it's the only method I'm going to teach you. So if you have another way, you're on your own. Okay, so we need to review those oxidation states. And like everything, have you ever sat down to play a new board game? You get a board game for Christmas, and you start reading the instructions, and you're like, oh my goodness, is there going to be a test? This is horrible. I don't know what it's doing. You read all these instructions or rules, and you're like, what is going on? But then once you learn how to play the game, and it starts to make sense to you, then you have no trouble remembering the rules, right? And you're even very happy to correct other players when they make a mistake. So, we just have to get through that part of the instructions being new. So any free element is going to have an oxidation state of 0. So you've got the element by itself. Doesn't matter if it's solid, liquid, diatomic, or not. Any element by itself, 0. Monatomic ions are going to have an oxidation state that's equal to their charge. So in sodium chloride, we recognize that there's a sodium ion and a chloride ion. The sodium ion has a +1 charge, so it has a +1 oxidation state. The chloride has a negative charge, it has a -1 oxidation state. The sum of the oxidation states of all the atoms have to add up to the charge of the thing, right? So if you have a compound, compounds are neutral. All the oxidation states add up to 0. If you have a polyatomic ion, polyatomic ion has a bunch of atoms in it, but it has an overall charge. Well, then the sum of the oxidation states adds up to the charge. In their compounds, metals have positive oxidation states, just like they have positive charges as ions. Group 1 is always +1, group 2 is always +2. And this is where we need to really learn something new. The rest of that all matches up with what we've learned about ionic charges. So, but what about the nonmetals? In molecular compounds, we've got nonmetals, and there are no ionic charges, but there can still be oxidation states. And so this table is the key to assigning oxidation states to nonmetals. No, why not? I'll just do it in the red. Pho. Everybody know what that is? Really good noodles, right? Pho. Pho 7-6. There's actually a restaurant, Pho 7-6. Let's stick a 5 on there and just going to erase a little bit of that P. Pho with an F instead of a P. 765. Fluorine, hydrogen, oxygen, Pho. 765. Do you remember that? Pho 765. So this tells us the order in which to give out oxidation states. What we're doing here is, we'll notice that the oxidation state of fluorine being -1 is the same as the charge it would have if it was an ion, right? And what charge would oxygen have? -2. The group 5 elements, like nitrogen, an ion would have a -3 charge. So the oxidation states here match the charge of the ion if it was an ion. That makes sense? And this list here is just who gets to choose first. So it's Pho 765. If there's a fluorine, he always gets to be -1. Then you next look at hydrogen, oxygen, and group 7, group 6, group 5. So you assign these, and then you come to the last element, and the last element has to make up the difference. If it's a neutral molecule, everything has to add up to 0. And so nitrogen might end up having to be +5, even though it wants to be -3, because of the other people, right? The other atoms. So any questions about that? The good news is that you can balance these half reactions, use the half reaction method without assigning any oxidation states. We do, though, need to be able to understand and recognize when something's being oxidized and something's being reduced. So here are the steps for half reaction method. Assign oxidation states and identify the substances being oxidized and reduced. That, that's a good thing to do, but I'm going to say that's actually optional. It's good practice, but it's not necessary. So we separate the overall reaction into 2 half reactions. One will be an oxidation, one will be a reduction. We don't actually have to identify which is which. Then we're going to balance each of the half reactions separately, first looking at mass, meaning number of hydrogens, the number of oxygens, same number of atoms of each element. Balance everything except hydrogen and oxygen first. Then, if there's some oxygens that you need to balance, you balance those by adding water, H2O. And after you get the oxygen sorted out, you balance hydrogen by adding hydrogen ions. So these reactions are a little funny because some of them, you look at the chemical reaction unbalanced, describing the oxidation reduction, and you're like, but wait a minute, this thing has an O in it, and there's no O on the other side. How can I possibly balance that? Well, all of this is happening in an aqueous solution, and water participates in the oxidation or reduction. So it seems like we're just like adding stuff just so it'll balance, but in truth, there's plenty of water molecules in there. And in acidic solution, there are going to be hydrogen ions around. So after you do that, then you balance with respect to charge. And we do this by adding electrons. So what we want to do is we want to make each side of each half reaction equal to the other side. We're just looking at two separate reactions, make sure the product and reactant side have the same total number of charge. If you end up with electrons on the same side for both half reactions, something is going wrong. Because one's an oxidation, one's a reduction, you'll end up with electrons as a product on one and as a reactant on the other. So now you've got two balanced half reactions. And now what we're going to do is we're going to make the number of electrons in both half reactions equal. And we'll see, that might be clearer when we do an example. And then we're going to add the two half reactions together. The reason that we're making the number of electrons equal is so that when we add them together, we have the same number of electrons on the product side and the reactant side. Because what happens is, as this reaction occurs, something is losing electrons and something is gaining electrons. And all the electrons that are lost have to be gained by the other thing. There's no homeless shelter for, those electrons that didn't get used in a redox reaction. That doesn't happen. If you need extra electrons, you can't go to the bank and take them out. They have to come from somewhere. So we add them together, canceling out the electrons and anything else that cancels. And then you should always double check, verify that it's balanced. So let's do some examples. And here this is like a short version of the instructions, right? So balance the redox reaction in acidic solution. So we could assign oxidation states. Well, let's just do that to review. What's the oxidation state of H+? +1. What's the oxidation state of Cr? 0. It's an element. How about H2? 0. And Cr2+? +2. So what's getting oxidized? Chromium is going up in oxidation state. And what's getting reduced? The hydrogen. Okay. So the electrons lost by chromium are going to be gained by hydrogen. So we're going to make two half reactions. And it's super helpful if you get their arrows to line up. So I typically just pick the first reactant and put that down for the first half reaction.
Quick question.
Yes.
Why is the oxidation state of the chromiums different?
Because the oxidation state of the chromiums is different because the chromium is being oxidized. Yeah, so it's gaining it's losing electrons in this process. And the hydrogen is gaining the electrons. So that really is the definition of a redox reaction. So we always have electrons going from somebody to somebody else. Usually it's not too hard to pick out what the other side of that one is. I mean, can you turn hydrogen ions into chromium? No. No, you can't. So this must be H2, right? And then that second reactant is solid chromium, and the one over here must be chromium ion. Okay, two half reactions. Balance with respect to mass. And this one's pretty simple. So here I've got one hydrogen and two hydrogens. So I need to add a coefficient of 2 to my hydrogen ion so that I have the same number of H's on each side. And here, a chromium and a chromium is already balanced with respect to mass. So we didn't have to get into adding any water or anything. Now we're going to balance with respect to charge. In this first one, there's a total +2 charge on the left and a 0 charge on the right. And we need to make them the same, and the only thing we can do is add electrons, which are negative. So I'm going to add electrons to the side that's 2 positive, or more positive. So I add 2 electrons here, and then I have -2 and +2 adds up to 0, which equals the other side. How many electrons do I need down here? I've got 0 on this side and +2 on that side. So I need 2 again, but they're going to be on the other side. What we can tell looking at these two half reactions, the chromium is losing 2 electrons. Oxidation is loss of electrons. The hydrogen ions, there's 2 of them, together they are gaining 2 electrons. That's the reduction. So this is a nice simple one to start with. We have 2 electrons and 2 electrons. They already match up. So now we're going to add them together. No, I don't want to do that color. So we're just going to add these 2 reactions together. And the electrons produced here got used up over there. There are 2 electrons on both sides of the equation, so we say they cancel out. And then you copy down what's left. And just like in adding, the order doesn't matter. And even mastering chemistry understands that. If you put the chromium first and then the 2 H pluses, it's exactly the same thing. Any questions? Is this at least vaguely familiar? Remember doing something like this? Let's do another one. No crib notes here. Let's look at this permanganate ion and look at its oxidation states just to practice that whole oxidation state business. So here, this is a polyatomic ion. Overall, it has a -1 charge. Now, manganese is a metal in here, but it's not an ion by itself. It's going to have a positive oxidation state, but we can't tell what it is. It's in the transition metals. It can actually have, I think there's like 7 different oxidation states it can have. So what do? Well, we're going to look at the oxygen. Because Fe765, there's no fluorine, there's no hydrogen, oxygen is next. What does oxygen want to be? -2. So I've got -2 for the oxygen, and how many oxygens are there? There's 4 of them. They are each -2. And so I need this to add up to -1. So what's the X? Heard +7 and +9. +7. Because this is -8, right? And if I've got +7 minus 8, I get -1. We look at that and we're like, I don't need a calculator for that. You might want to just use your calculator because it's so easy to get those things backwards. And it's a shame to miss a problem because of that. Yeah, so the manganese here is a +7. And over here, the manganese is +2. So we can see that's the thing that's being reduced. Iron is going from +2 to +3. That's the thing that's being oxidized. Okay, 2 half reactions. Fe2 plus. And I'm going to pick the product that is most similar to it, which is the Fe3 plus. And then down here I've got my permanganate ion and my manganese ion. Balance for mass first. First equation, 1 iron, that one's fine. Here I've got 1 manganese and 1 manganese, that's all good, but this side has 4 oxygens, and there's nothing with oxygen over here that I can mess a coefficient with, right? So you balance everything but the oxygen and hydrogen first. You balance the oxygen by adding water, because this is happening in water. So I'm going to add H2O. And I'm going to do that so the oxygens balance. I got 4 oxygens here. That means I need 4 water molecules. We fixed the oxygen and introduced a different problem, hydrogen. So we're going to fix the hydrogen last because we're going to add H pluses, and that's not going to mess anything else up. So over here, I have a total of 8 hydrogens. So that means I need to put 8 hydrogens on the other side. These are going to be hydrogen ions because this is an acidic solution. Okay? Now we balance for charge. What should I do to this first one? How many electrons? 1. Which side?
Right side.
The right side. So if I put 1 electron over here, these add up to +2, and that's +2. This one's a little messier. And it might be a good idea to actually just like write it down. So I've got +8, and I've got -1, right? So that's giving me +7. And then over here I have +2. So I need 5 electrons on the left side to make the charges equal. You see that? Now I've got -5 and another one, so that's -6, and +8 adds up to be the +2.
We don't count the water because it's a neutral compound.
The water's a neutral compound, right? So this has no charge on it, so it doesn't contribute anything to the charge. So this half reaction is losing 1 electron, but this one is gaining 5 electrons. So we're going to need 5 times the number of these guys reacting to give us the electrons for one of this reaction to go. I'm going to look at my numbers of electrons. I've got 5 and 1. I'm looking for the least common multiple so I can get them to be the same. So I can multiply 1 by 5 and get 5. So I'm going to multiply this top one by 5. And I'm going to multiply all the coefficients by 5 so that it remains balanced. So it's going to be 5 of those and 5 of these and 5 electrons. Still balanced. Now we add them together. The electrons should always cancel out. And then I'm going to copy down what's left. 5 Fe2 plus 8 H plus MnO4 minus aqueous gives me 5 Fe3 plus and then 2 plus. It's not tedious at all. So there's my balanced equation. The previous slide, you could have done that one by inspection. This one, no, you couldn't. It'd be really tough. Any questions?
Are we not reducing the H pluses with the hydrogens in the water?
That's a good question. Are we not reducing? We've got 8 H's, H pluses over here, and we have 8 hydrogens over there. They are not the same, so they don't cancel out.
Okay.
Yeah. Yeah.
Is it just because you need the oxygens or the other side? Is that-
Yeah, I added the water here because I needed oxygens in here somehow. Yeah. Mm-hmm.
So the charges, like for the example, the 2 plus and the 3 plus for the iron are gonna be given in the equation?
Yeah. Yeah, you'd be given something like this.
Okay.
Yeah. Because, I mean, there's a lot of different possible combinations that could happen. Iron can go from, 0 to +2, or 0 to +3, or the other direction. Yeah. Here's another one. So, again, I'm going to just do the first one first. And the second one second. And it helps if you leave a little space in here, recognizing that I might need to put some coefficients in there at some point. Mass first, the letters. So I got Cu and Cu, that one's good. Over here, I have 1 nitrogen and 1 nitrogen. I've got 3 oxygens here and 2 oxygens there. Without adding water or something, there's no way you can balance that, right? Because the nitrogens are fine, but the oxygens are not. So to get 3 oxygens on the right side, I'm going to add water. So I've got 3 oxygens and 2 plus 1, 3 oxygens. Now I introduced hydrogen, so I have to take care of that. I've got 2 hydrogens in here. I'm going to balance those by adding 2 hydrogen ions. Next, I'll balance for charge. So this top one, I've got +2 on this side and 0 on that side. So how many electrons do I need? I need 2 electrons. If I put 2 electrons over here, then +2 and -2 adds up to 0. Same charge as on the other side. A lot of times they add up to 0, but not always. They just need to be the same. Then down here, everything on the product side is neutral. So that's going to be 0. But I have a -1 here, and I have 2 positive charges there. So what do I need? 1 electron. So here's 2 negatives and 2 positives, adds up to 0, same as the other side. I want to add these together so that the electrons cancel out. What's the least common multiple of 2 and 1? It's 2. So I'm going to multiply this one by 2. So it's going to give me 2 electrons, and the hydrogen's going to be 4, and this is going to be 2, and this is going to be 2, and that's going to be 2. You have to apply it to everything because we had it balanced, right? We had the charge and the mass balanced, and we don't want to mess it up. So if we multiply everything by 2, we're good. So now we can add these together. So 2 electrons being lost over there, 2 electrons being gained over there. The electrons are moving from one thing to another. That does not show up in the overall chemical reaction. Does anything else cancel out? No. So solid copper plus 4 hydrogen ions plus 2 nitrate ions copper 2 ions, 2 NO2s, and 2 H2Os. Then you should always go through and double check that. So you know that permanganate and iron, those permanganate and oxalate thing you had to balance for the lab? I mentioned this, but I don't think anybody really understood what I was saying. That's exactly the same chemical reaction you did for your lab practical in Chem 1A. And if you go and look at the Chem 1A lab information, the balanced chemical equation is there. So
But we wanted to do it the hard way.
we wanted to do it the hard way, and it was good practice. And now this is going to make so much more sense. So that's why I was like, no, I'll just let them do it. It's fine.
Thank you for letting us suffer.
Yeah, gotta have some fun. So what if we have a basic solution? We add one step. When you're balancing here, after you balance the hydrogens by adding hydronium ion, you're going to neutralize the hydronium ions with hydroxide ions. So if you have 4 hydrogen ions on one side, you're going to add 4 hydroxide ions to each side. It's still balanced, but now it doesn't have any hydrogen ions in it. It's got hydroxide ions. Okay? And you can do that in the mass balancing part, or you can do that at the very end. It all comes out the same. These get a little messier because we end up with things we have to cancel more often. So balance this redox reaction in basic solution. So 2 half reactions. One for iodide going to iodine. And one for permanganate going to manganese 4 oxide. So I'm going to balance for mass. I have 2 iodines on one side and 1 on the other, so I'll put a 2 here. My mass is balanced. I have 1 manganese and 1 manganese, 2 oxygens and 4 oxygens. So I need to add 2 water molecules to this side to get the number of oxygens to be the same. And then I'm going to balance the hydrogens with H+. And sometimes students will say, well, why do we have to do that? Couldn't we just go straight to the hydroxide? It's fraught with peril, because there you have hydrogens and oxygens, and you're going to make yourself crazy. This is one little step that makes it so much faster, so don't try to get fancy. So here, 4 hydrogens. So I'm going to put 4 hydrogen ions over there. This is where we pay attention to this is happening in basic solution. Are there hydrogen ions floating around in a basic solution? No. But there's hydroxide ions, right? So if I add 4 hydroxide ions to this side, what do these guys make? 4 H2Os. So these guys call 4H2O. If I want this to be balanced, I have to add the same thing to the other side, 4 hydroxide ions. Okay? Now we'll go for charge balance. I have -2 over here and 0. So I'll add 2 electrons. On this side, I have -4. And on the other side, those guys took each other out, so that was nice. I have -1. So if I add 3 electrons to this side, then it'll be good. Let's see if it'll let me do this. So I have 3 electrons. Okay? If you want to cancel out the water molecules here, you certainly can. In this one, there's no water in the other half reaction, so you could just take care of it now. Sometimes there's water all over the place, and even if you take care of it here, you end up canceling things out later anyway. How do we make the number of electrons equal? We're gonna have to go to 6, right? So I'm gonna multiply the top by 3 and the bottom by 2. And I learned to write this out because as I'm going across, even when I'm saying it out loud to myself, I keep messing up. And so then I can go back and look, what am I doing? Okay, so times 3. So times 3, this becomes 6. Times 3, that becomes 6. Then down here, times 2, that's a 6. Times 2, that's an 8. That's a 2. That's a 2. Times 2 is a 4. Times 2 is an 8. This is not something you can do in your head. I can't. So now we can add things together. So I have 6 electrons on each side because I made it that way. And then I'm going to copy down what's left. You want to cancel the waters out now? So I have 4 waters on this side and I have 8 on that side. I could subtract 4 water molecules from each side and it'll still be balanced. Does that make sense? So this is going to become 4 and that's going to become none. So 6 I minus plus 4 H2O liquid plus 2 permanganate ions. It's going to give me 3 iodine molecules and 2 MnO2 and 8 hydroxide ions. Any questions? Let's do another one. You can never have too many redox reactions. No, that's not quite true. So I've got ClO minus And I've got Cl minus over here. How would we figure out the oxidation states of chlorine and oxygen in here? Oxygen first, Fe765. No fluorine, no hydrogen, oxygen. Oxygen's going to choose what? -2. And so then the only thing left is chlorine, so chlorine has to make up the difference. So chlorine must be +1. It's an unhappy chlorine, exactly. You think chlorine's happy with that? No. No, it's not. And so this reaction is going to go, and chlorine's going to end up being -1, which is what it really wanted in the first place, but, you know, he was second to the oxygen. There's all sorts of nitpicking and petty fighting in my chemistry world. Probably reflects living with children for so long. When they were all small and I was wrangling them at church, the old ladies would say, "Oh, enjoy it, honey, it goes so fast." I did the math. 32 years of a child in my house.
You're not over.
I'm not done yet. No, I got a good 4 years left. But right now I only have one at home. Okay, I drew a line prematurely. Okay, got distracted, sorry. Okay, we got our half reactions. What do we do next? Balance for mass. So 1 chlorine and 1 chlorine. How do I fix that oxygen issue? Add H2O. Just add water, right? Now what do I do? I need how many H's? 2. I need 2 H pluses. And now I'm good. Down here, 1 chromium and 1 chromium, 4 oxygens and 4 oxygens. That's kind of nice. But I got 4 hydrogens here. So I'm going to add 4 hydrogens over here.
For the top row, since it's a basic solution, do we not need to add hydroxide to the other side?
Well, that's a good question. I think most people prefer to take care of that acid-base thing right away. And so we're still in the balancing for mass thing when we realize, hey, wait a minute, this is a basic solution. I can't have hydrogen ions all over the place. So I've got 2 hydrogen ions here. If I add 2 hydroxide ions, what do those become? 2 water molecules. So I hope this doesn't freak anybody out, but I'm just going to make that into 2 water molecules. And what did I have to do the other side? The same thing. I added 2 hydroxides, so I need to add 2 hydroxides over here. It's important not to forget that part. I almost did. How many hydroxide ions do we need to add to the bottom equation? 4, because I have 4 hydrogen ions. We're just adding the same number of hydroxide ions. So if I add 4 hydroxide ions, this is going to become 4 water molecules. And I'm going to have the 4 hydroxide ions over there. Okay? So my mass is all figured out. Now I'm going to look at charge. Here I have a -1 and 2 -1s, so that's -3 and -1 over there. That tells me I need 2 electrons. And you can think that out, but then always just kind of look at it again. Okay, -2 and -1 is -3. Okay, -1 and okay, right? It's so easy to mess that up. Down here, we've got -4 and another one, so that's -5. And over here I have -2. So I'm going to need 3 electrons down there to make them the same. You should always have electrons on the left as a reactant for one and as a product on the right for the other. And if you don't go any further. Go back and figure out what went wrong. Now I want to add these together so that the electrons cancel out. So I've got 2 and 3, so I can get them both to be 6. But that's no good. So the button's too close to where I'm writing. I'm going to multiply this by 3, and I'm going to multiply that one by 2. So this is 6, and 6, and 3, and 3, and 3, and 6. Bottom one, I'm multiplying by 2, that becomes 8, and 2, and 2, and 8, and 6. At least we never have to do like 12 times 14. This is little numbers. I'm pretty hopeless after I get past 11s. Some 12s I can do, but some of them not. Okay, so adding these together, we've got the electrons that are going to cancel out, 6 on that side, 6 on this side. Now we can also look and see what else is going to cancel out. H2O. I've got 6 H2Os on this side, and I have 8 on that side. So we could get one side down to no water molecules. I'm going to subtract 6 from both sides. So this is going to end up with no water molecules, and this one is going to end up with 2. Okay? What else shows up on both sides? Hydroxides. So I've got 6 hydroxides over here, and I've got 8 over there. So if I take the smallest one and I subtract that from both sides, then I'm going to get 2 hydroxides in the bottom. When we're doing stuff like this, this is when it becomes a little more important to check the final thing at the end and make sure we didn't mess something up. Okay, so 3 ClO and 2 hydroxide and 2 of that guy that we'll learn how to name in chapter 26. And 3 Cl minus, 3 H2O, and 2 chromate. And then I've got another 2 down here. Well, that's nice because I wasn't having enough space. So I'm going to add the 2 to the 3 and get 5 here. I made it on one line that time. And then you can go back through and double check. Isn't that fun? Oh yeah. Any questions?